we have a test here for testing whether a function is increasing or decreasing. Suppose a function f has a derivative at each point in the interval. Then, if f prime, the derivative, is greater than 0 for each x in that interval, then the function's increasing because the slopes are positive. If x is less than 0 for each x in the interval, then it's decreasing. And if the derivative is equal to 0, then we know it's constant in that interval. Now, to help us use this test, we're going to talk about something called a critical number. And what a critical number is it's a place where the derivative is equal to 0. So if I can take the derivative and find a value for x, which we're going to call c, where the derivative is equal to 0 or it does not exist, then that's what we're going to call a critical point. Along with the critical point is the y value, so the x coordinate would be called the critical number. The critical point is the x and the y coordinate. And you'd get the y coordinate by putting the critical number into the original function. So to apply this test, what we're going to do is step 1, we're going to locate the critical numbers for f on a number line, as well as any points where f is undefined. These points determine several sections or open intervals for that function. In step 2, we'll choose a value of x in each one of those open intervals or in each one of the sections that we found in the number line from step 1. We'll then go ahead and plug those values into the derivative to figure out if in that section the derivative is greater than 0 or less than 0. The reason why we do that is because if it's going to change from positive to negative, it's going to go through one of the critical numbers where the derivative was either 0 or undefined. Once we've made up that number line, then we'll be able to look at the values of the derivative to decide if it's positive, f is increasing. If it's negative, then f is decreasing. In this example, we want to find the intervals in which the function below is increasing and decreasing. And this function is f of x equals 2/3 x cubed minus x squared minus 24x minus 4. Let's follow those steps that we just outlined. So we'll start by locating the critical numbers by setting the derivative equal to 0. So our derivative, when we take the derivative of the x cubed, it gives us x squared times 3. Multiply that by 2/3, we get 2x squared. The derivative of x squared is simply 2x, and the derivative of minus 24x is minus 24. The derivative of this last term, negative 4, is 0, so that's why it doesn't appear in the derivative. Set that equal to 0 gives us 2x squared minus 2x minus 24 equals 0, and that's a quadratic equation, so to solve that, we're going to need to do some factoring. First thing I'm going to do is go ahead and factor out the 2 to make it a little bit easier, and then after that, I'm going to notice that I can break this up into a binomial times a binomial. It's going to be x times x, and then last times last to give me minus 12, and add to negative x, that means I'm going to need a minus 4, so the inside term is minus 4x, and a plus 3, so the outside term is plus 3x, and those add to giving me minus x. We have 2 times x minus 4 times x plus 3 equals 0. To finish this, we're going to need to set each one of the factors equal to 0. We don't need to worry about the 2 because 2 can't equal to 0. But we can set x minus 4 equal to 0 and x plus 3 equal to 0. When we solve those for x, we get 4 and negative 3. So those are the numbers that we're going to put on our number line that break it up into those open intervals, into those sections. So I've gone ahead and I've written out a number line here, and I've labeled on that -3 and 4. And above here, I've written equals 0 because that's where the derivative was equal to 0. The next thing we need to do is to test in each one of these sections the derivative to figure out whether it's positive or negative. So let's start out with -5, and I'm going to need to put -5 into the derivative. When I do that, the first factor here is -5 subtract 4, that's negative. The second factor is -5 plus 3, that's also negative. So 2 times a negative is going to give me a positive. Notice I really don't need to know what the numbers are. I just need to know whether they're positive or negative so that when I multiply them, I know what the final product is. So in the first section, I just got a positive value, and it's going to be positive everywhere in here until possibly it gets to where it's 0. Here is where it might change. So I'm going to pick another number in this open interval. So between -3 and 4 is 0, and now I'm going to put that into the derivative again. So 0 into the first factor is negative, 0 into the second factor is positive, 2 times a negative times a positive is negative, so up in this section, I'm now going to get that it's negative. If I go into the last section, I pick a number, in this case +5. When I put that into the derivative, I get 2. 5 minus 4 is positive. 5 plus 3 is positive. So 2 times a positive gives us a positive. So I'll write that out on my number line up here. So now I know everything there is to know about this derivative. It starts out positive, changes to negative when we go across -3, changes back to being positive when we cross 4. So if I want to know where this is increasing, that's where the derivative was positive. So that means I'm going to be in the section from -infinity to -3, or from 4 to +infinity. It's going to be decreasing in between. So from -3 to 4, it's going to be decreasing. Be real careful when you write this out, because you're tempted to use the 5, the 0, and the -5 to write this out, but the borders of where it changes from increasing to decreasing always occurs at the critical numbers, which in this case are -3 and 4. If we look at the graph, you can see exactly what we just found. Remember, we said it was increasing up until -3, and then it's decreasing until 4, and then increasing again after 4. Let's try the same process, but now let's try it on a function f of x equals x plus 2 divided by the quantity x plus 1. So again, we're going to have to locate the critical numbers by setting the derivative equal to 0, and remember, critical numbers could also be where it's undefined. So let's take the derivative. Remember, this is going to require quotient rule. So the top's u, the bottom's v, and the u prime is going to be 1. The v prime is also going to be 1. And let's put that into our quotient rule. So we get v u prime, which is x plus 1 times 1, minus u v prime, so the quantity x plus 2 times 1, all over v squared. So x plus 1 squared. I'm going to go ahead and distribute that negative onto each one of my terms here. And when I do that, a lot of good stuff happens on top, and we get -1. On the bottom, we still have x plus 1 squared. To find my critical numbers, I'm going to set that derivative either equal to 0 or undefined. Now, if you look at a fraction is going to be 0 when the top's 0, and this fraction is never 0. It's always -1. So the only critical numbers we're going to get here is when it's undefined, and that's where the bottom's equal to 0. When I set x plus 1 equal to 0, I get x equals negative 1. Our next step is to go ahead and make our number line, and I've labeled negative 1 on this number line. It breaks me up into two sections, and above I've written undefined to indicate that the derivative was undefined there. Now we need to go ahead and do our testing. So I'm going to test at negative 2, and when I put negative 2 into the derivative, on top is negative 1. When I put negative 2 into the bottom, I get a negative number, but it's squared, so that means the bottom here is going to be positive. Negative divided by positive is going to give me negative. I'll go ahead and label that on my number line. When I test on the other side, I'm going to pick the value of 0 because it's easy to work with. And now I have to find f prime of 0. When I go ahead and put 0 into x plus 1 squared, it comes out to be positive again. Negative 1 divided by positive is going to be negative, so that means that we get a negative on the right-hand side of the critical number. One of the things that students often do is they get into this mode of if you find what happens in one place on the number line, you assume at every critical number the signs alternate. But in this case, the signs don't alternate. It's negative on the left-hand side and negative on the right-hand side, meaning this function decreases everywhere except at negative 1 because it's not defined at negative 1. So it's decreasing from negative infinity to negative 1, union negative 1 to infinity. Notice that we've left out the negative 1 because of the parentheses. You might ask yourself, well, how could that possibly happen on a graph? Well, here's the graph. On the left-hand side of the asymptote, which is at negative 1, the graph is dropping, so it's decreasing. And on the right-hand side, it's also decreasing. So this is not uncommon when you have asymptotes in something like the function we have, which is a rational function.